Remember that when building a regression model, we have a lot of choices to make in terms of what that model looks like. In this video series, we'll explore the LASSO algorithm and how it can help us automate the model selection process. This is a two-part video series. Naturally, let's start with part 1 and some motivation. Suppose we wish to build a good predictive model of height using the data here on 20 subjects and the 19 possible predictors shown here. These predictors include abdomen circumference, wrist circumference, and 17 nonsense variables, x3, x4, up to x19. These nonsense variables are simply collections of random numbers. Now, if we use too many predictors in our model, we risk overfitting the model to our data. But if we use too few, we risk ignoring important information about height. There are 3 general model selection techniques that can help us out here. We've already discussed the first of these, variable selection, which identifies a subset of predictors to use in our model of y. The second, which we'll discuss later this semester, is dimension reduction. The idea here is to obtain a smaller set of new predictors, not by kicking out any of our original predictors, but by combining them into a smaller set of predictors. In this video, we'll explore an alternative set of techniques for model selection, shrinkage and regularization. In short, these algorithms perform model selection by shrinking the predictor coefficients toward or to 0. There are multiple possible methods here, but we'll focus on the LASSO. First, recall our general goal. We want to build a regression model of height using a set of available predictors x. We do so by using our sample data to estimate the beta predictor coefficients, denoted here by beta hat. We've taken this for granted, but it turns out that there are lots of strategies for picking these coefficient estimates. Up to this point, we've only used one approach to linear regression in Stat 155 and 253, the least squares algorithm. The idea behind this algorithm is simple. We want our overall model prediction errors to be as small as possible. To make this dream a reality, we must translate this goal into a mathematical rule or criterion. To this end, the least squares algorithm identifies the coefficient estimates beta hat which minimize the model's overall prediction errors, as measured by the residual sum of squares, or RSS. Let's break down this notation. RSS calculates the squared residual, or prediction error, for each subject in our sample, from subject 1 to subject 2, all the way up to subject n, where n is our sample size. Then, to assess the overall prediction error, not just the error for each individual, RSS sums up these squared residuals. Finally, the sum of the squared residuals is written using the summation notation at left. In words, RSS sums the squared residuals for subjects I, where I goes from 1 to n. We'll use this shorthand in the remainder of the video. Shown here are the results of using the least squares algorithm to build our regression model of height by all 19 of our possible predictors, including abdomen, wrist, and the 17 nonsense predictors. Recall that these particular predictor coefficients were chosen to minimize the residual sum of squares. In fact, we were so successful that the RSS, hence the combined prediction errors, are exactly 0. That is, this model produces perfect predictions of height for our 20 sample subjects. Correspondingly, the model has a perfect R-squared. It explains 100% of the variability in height from person to person. At first glance, this seems exciting, but if we step back, there are signs that this model is problematic. First, the reported RSS and R-squared are in-sample metrics, thus don't describe how well our model would perform on new subjects. In fact, by optimizing a model with all 19 predictors to only 20 subjects, this model is most certainly overfit to our sample data. Finally, 17 of our model predictors are random and have nothing to do with height. This all reveals a drawback of the least squares approach. When working with many predictors, the least squares algorithm can produce misleading, overfit models. Yikes. In cases where we're working with lots of predictors, the least, absolute, shrinkage, and selection operator, or LASSO algorithm, provides an attractive alternative. Conceptually, just as the spaghetti noodle here is reining in a runaway meatball, the machine learning LASSO technique reins in runaway coefficients. The goal behind the LASSO is the same as for least squares: to build a regression model of some response variable y by predictors x. In working toward this goal, the idea behind the LASSO builds upon that behind the least squares. Not only do we want to make the overall model prediction errors as small as possible, we want to do so without overfitting our model to the sample data. To achieve this modified goal, the LASSO utilizes a modified criterion. Specifically, instead of seeking coefficients that minimize the residual sum of squares, as happens in least squares and doesn't address overfitting, LASSO seeks to minimize a penalized residual sum of squares. I expect this looks quite strange and unintuitive, so let's pick it apart. The penalized RSS used by the LASSO algorithm has two main components. The first is just the unpenalized RSS as used by least squares, which measures the model's total squared prediction errors. The second is the penalty term in red. This penalty term adds up the absolute values of the beta hat coefficient estimates for our p predictors. Thus, it captures the total size of the p predictor coefficients. It then multiplies this sum by the parameter here, represented by the Greek letter lambda. Lambda is a tuning parameter for the LASSO algorithm, which can take any value greater than or equal to 0. In fact, when lambda equals 0, the penalty term simply drops out of the criterion. Thus, at this extreme, we're left with the RSS, meaning the LASSO algorithm is equivalent to least squares. Putting this all together, the LASSO algorithm identifies coefficients for which the following factors combined are minimized: the model's total prediction error and the model's total coefficient size. Now, if you're like me when I learned the LASSO, you're probably thinking, it makes intuitive sense that we want small prediction errors. But why do we care about coefficients? Thus, what's the point of this penalty term? The idea is this. The penalized RSS allows the LASSO algorithm to identify which predictors are more important to the model. First, a good predictor helps improve our model predictions, thus decrease the residual sum of squares. And when the predictor is good enough, the decrease in RSS will offset the penalty for including this predictor in our model. In contrast, a bad predictor will improve our model's in-sample predictions, every predictor does, but not in a meaningful way. Thus, though a bad predictor will lead to a small improvement or decrease in the residual sum of squares, it won't be substantial enough to offset the penalty incurred for including this bad predictor in our model. To build some intuition for this theory, let's use the LASSO algorithm to build a regression model of height by all possible 19 predictors. To begin, let's run the LASSO using a tuning parameter of lambda equals 0. The coefficients shown here minimize the penalized residual sum of squares when lambda equals 0. But recall that with a 0 penalty term, these LASSO coefficients are equivalent to those obtained by the least squares algorithm. So let's crank up the tuning dial a little bit, increasing lambda to 0.0001. By picking a non-zero lambda, we're starting to actually penalize the total size of our model coefficients. Now, pause your video for a moment to compare the LASSO coefficients when lambda equals 0.0001 to those when lambda equals 0. What you might notice is that all of the coefficients have been squeezed closer to 0. That is, they've shrunk. As one example, the abdomen coefficient dropped from 13.02 to 9.2. This shrinkage is explained by the penalty term. The LASSO model is trying to balance a desire for small prediction errors with a desire to minimize the total size of the coefficients. If we crank lambda even higher, to 0.01, we put an even greater penalty on the total size of our model coefficients. Thus, they shrink even closer to 0. In fact, the coefficients of two of our junk predictors have shrunk all the way to 0, thereby kicking these predictors out of the model. As we continue to crank lambda to 0.1 and 1, the coefficients shrink even more, and even more of the junk predictors are kicked out of the model. By the time that we crank lambda to 2, all of the junk predictors have been kicked out of the model, and all that remains are our two meaningful predictors, abdomen and wrist. This is essentially what we anticipated earlier. These bad predictors might improve our in-sample model predictions, but not enough to offset the complexity that they add to the model, hence not enough to offset their LASSO penalty. Of course, we bear the risk of going too far. At some point, if we tune lambda to be too big, all predictors are kicked out of the model and we're left with nothing. So clearly, picking the right lambda is crucial to implementing the LASSO. Let's summarize what we've learned. In general, the LASSO algorithm builds the linear regression model, which minimizes the penalized RSS. And how this criterion plays out greatly depends upon the tuning parameter lambda. First, we observed that as lambda increases, large model coefficients are increasingly penalized. Thus, they shrink and shrink and shrink towards 0, becoming regularized. It is for this reason that LASSO is called a shrinkage or regularization algorithm. Second, we observed that picking an appropriate lambda value is a Goldilocks problem. We don't want lambda to be too small or too large, but just right. For example, when lambda equals 0, that is, too small, the LASSO is equivalent to least squares. That is, it doesn't help simplify our model or help with model selection at all. At the other extreme, we observe that when lambda is too big or ambitious, it kicks all predictors out of our model, even the good ones. Thus, we must strike a balance. When lambda is neither too big nor too small, but just right, the LASSO algorithm does what we want it to do. It helps with model selection. Specifically, it helps build a parsimonious model, one with a streamlined set of good predictors that produce quality predictions. We also have more to learn about the LASSO. In part 2 of this video series, we'll address an important detail that we've ignored here.